We're going to start the section that talks about adding and subtracting fractions. We're going to start first with adding and subtracting fractions with identical denominators. That's on page 22 in your book. So we have two cases when we add and subtract fractions. The first case is going to be when you have identical denominators. When you have identical denominators, the procedure is very easy. We have one fraction, a over b, plus another fraction, c over b. So the first thing that you check is that you have the same denominator in both fractions. So to solve this problem, you're gonna just get a fraction bar, and you're gonna write the common denominator, and then you're gonna write the numerators, the sum of those numerators. So it's gonna be a plus c. So what you're gonna do then is you need to write the sum or difference, because we're gonna see that it's the same thing when you are working with the difference of two fractions. You're gonna write the sum or difference of the numerators over the common denominator. Then you just simplify. Then you're gonna perform the indicated operations. Operations and simplify. So remember, we want always the fraction in its lowest terms. So if you have a over b minus c over b, and you check that you have the same denominator, then you just write that common denominator as your denominator for the difference, and you write that difference on the top, the difference of the numerators. So we're gonna work one example. This is gonna be example 7. Is also on page 22, and the directions are just perform the indicated operations. So the first case is gonna be 3 over 11 plus 4 over 11. So you can see here that you have the sum of two fractions, and the first thing that you check is the denominator of the first fraction, then the denominator of the second fraction, and you see that the denominators are the same, is the same number. So you're gonna get that common denominator here, then you're gonna write the sum of the numerators on the top, and then you simplify. So you're gonna get 7 over 11. Now we have a difference, so we have 11 over 12 minus 5 over 12. You check, we have the same denominator, so we write 12 here, and then we write the difference, 11 minus 5. We proceed with this indicated operation. 11 minus 5 is just gonna be 6 over 12, and then you just try to check whether we have a common factor between the numerator and the denominator. You note that 6 is divisible by 3 and 12 is divisible by 3, then you just divide by 3 here, divide by 3 here, so you're gonna get 2 over 4, and you still see that there is another common factor between the numerator and the denominator, so that common factor is 2. So you're gonna divide by 2 both the numerator and the denominator. Remember, anytime that you divide or multiply the numerator, you need to multiply also the denominator by the same quantity. So 2 over 2, or 2 divided by 2 is gonna be 1, 4 divided by 2 is gonna be 2, so the final answer is just 1/2. We have now a problem that involves mixed numbers. So this is just for completeness. Remember, we are not going to deal with mixed numbers in our class, but this is part of the example, so we're gonna solve this example. The first thing is that these are mixed fractions, mixed numbers. So we're gonna convert this into improper fractions. So how do you do that? You just check the denominator that you have for the fraction part. Then you multiply the denominator and the whole part. So 4 times 5 is gonna be 20, and you add the numerator in the fraction part. And you're gonna do the same thing with the other one. So the denominator is gonna be 4. 4 times 2 is gonna be 8, and you add the numerator that was already there. Then we simplify the operations on the top of each fraction. So you have 21 over 4 minus 11 over 4. Now, this is the problem that we are learning to solve here. So we're gonna see that we have the same denominator. So we're gonna write a common denominator, which is gonna be 4. Then we write the difference of the numerators. Then we proceed with the computation. So you're gonna get 10 over 4. And then you just check whether you can simplify the fraction, which means that if you can reduce the fraction to its lowest term. So you're gonna see that a factor of 10, a common factor of 10 and 4 is gonna be 2. So you divide by 2, both the numerator and the denominator. So you're gonna get 5 over 2. So this is the final answer for us. For the book, you need to convert this improper fraction into a mixed number again. But for us, that's what we need to know. So this is the way that we solve fractions anytime that you have the same denominator for every fraction in the program. But this is not the usual case. So most of the time, you're gonna have different denominators. So we're gonna learn now how to solve problems when the denominators are different. So this is the second part of this section about addition and subtraction. So this is gonna be the case when you have unlike denominators. So when you have different denominators, so you might have learned in school the bow tie method. We're not going to use that method now. We're gonna use just the LCD method. The LCD method is the least common denominator method. So this is on page 23 in your book, if you want to read that part of the section. So we're gonna just write a simple steps. So the first step is you're gonna need to obtain the prime factorization of the denominators, What is this prime factorization? Is just that you're gonna write, so you're gonna express, so write every you're gonna write every denominator as the product of prime numbers. So that's the prime factorization. What are the prime numbers? If you don't remember, the prime numbers are just 2, 3, 5, 7, 11, 13, 17, 19, and an infinite number of numbers that you can just divide the number by itself or by 1 to get an integer. So there are no other, these numbers, they don't have other factors than themselves and 1. So then once you obtain the prime factorization, what you're going to do is you're going to compose the least common denominator by incorporating the factors, the distinct factors at their highest power that were obtained, or that are part of the denominators. So we're going to see how to do this by solving some examples. So once you do that, the last step is you're going to rewrite. You're going to rewrite the fractions to have the same denominator. So how? By multiplying the fraction by the factors, the missing factors. What is the missing factor? So this is something that is better understood when we solve examples. So let's solve example 9. So I'm just writing this rule. This is these steps are just for you to have in your notes. Once you understand the example, you go back and read this, and you're gonna see that these steps make sense. So the first case from example 9 is case A, is just 1/5 plus 3/4. So what do you do first? You check the denominators, right? And you see that these denominators are different. So we have different denominators. So we need to write every denominator by using only prime numbers. So 5 is going to be just 5 because 5 is a prime number. So this is going to be my prime factorization of the denominators. So this is the first one, 5. What about 4? 4 can be written by writing 2 times 2. These are prime numbers. So you're going to write this as 2 to the second power. So this is the prime factorization of 4, and this is the prime factorization of 5. So now we're going to compose the least common denominator. So what is the least common denominator? It's going to be just the product of the distinct factors. So the least common denominator is the product of the distinct factors. The distinct factors at their highest power. So in this case, I have 5. And then the next one is going to be 2 square. So this is the least common denominator. We're going to write just the least common denominator as 5 times 4, because 2 to the square is just 4. So this is the least common denominator written by using the primes, the prime factors, or the prime numbers. And this is just the least common denominator written as using just the resulting factors. So 5 times 4. So, and this is 20. So the least common denominator is 20. So we're going to write the third step is we're going to rewrite the fractions by using the least common denominator for each fraction. So we're going to rewrite this fraction. So 1 over 5 is going to be multiplied by something, plus 3 over 4 is going to be multiplied by something, and in that way we're going to get the least common denominator for every fraction. So I need 20 here. So what is the factor? 5 times 4 gives me 20, and since I multiply the denominator by 4, I need to multiply the numerator by 4. In this case, how do I get 20? Multiplying 4 by what? By 5, right? So I need to write 5 here, 5 here. So now I'm going to get 4 times 1 is going to be 4 over 20. And I'm going to get 3 times 5 is going to be 15 over 20. So now I have my two original fractions written by using the least common denominator. So in other words, I'm going to simplify, I'm going to just summarize the word that we just did. So we have 1 over 5 plus 3 over 4 became 4 over 20 plus 15 over 20. So this sum is equivalent to this sum. The only difference is that we move from having different denominators to have now a common denominator, the same denominator. So now it's very easy to solve this problem. We're gonna do what we did before. So we're gonna write the common denominator. We're gonna write the sum on the top of this fraction, and then we're gonna get the final answer. So we're gonna get 19 over 20. So that's the final answer. So let's continue using this new method, the least common denominator method, now with the difference. So we're gonna subtract 1 over 6 from 3 over 4. So first, we have like denominators. So we have different denominators. So we need to write, we need to find the prime factorization for this denominator. So what is the prime factorization? For this one is 2 squared. We know that already. For this one, 6 is going to be 3 times 2. So these are our prime factorization of the denominators. Okay, so now the least common denominator. The least common denominator, which is the second part, we're going to compose the least common denominator. The least common denominator is going to be the unique factor. So we have 2. We have 2 here. So we have this prime number appearing here and appearing here. But in this case, we use the highest power. So 2 to the second power is the way that we're going to write this prime number, number 2. The other prime number that is present in these denominators is 3, and that's it. So this is going to be 4 times 3, so this is going to be 12. 12 is our least common denominator. So anytime that you have a prime number appearing in every denominator, you're going to pick the one that contains the highest exponent. So this is just the only thing that you need to check carefully. The rest is just writing the other distinct prime numbers that you're going to find in these prime factorizations. So once you have the least common denominator, you're going to rewrite the fractions, the original fraction, by using the least common denominator. So we have 3 over 4, and we're going to multiply 3 over 4 by something, minus 1 over 6. We're going to multiply this by something. And what is that something? So in the first case, I need to get 12. So I'm going to multiply 4 by 3 and by 3 here. In the second case, I need to multiply 6 by 2, and then here by 2. So check that you have the same number both in the numerator and the denominator, the same number in the numerator and the denominator. Otherwise, you're going to make mistakes. So once you have this, you just complete this process. 3 times 3 is going to be 9. 4 times 3 is going to be 12, minus 1 times 2 is going to be 2, and 6 times 2 is going to be 12. Now we see that we have the same denominator, and also that the same denominator is the least common denominator. So we write the least common denominator, we write the difference of the numerators, and we finish this process. So we're going to have 7 over 12 as our final answer. So that's example 9. We're going to work one more example, and then you might have some work to do. So we're going to work now example 10. That example is on page 25, and this is just 1 over 15 plus 7 over 24. So first, we need to check that we have unlike the denominators. So we need the prime factorization. We need a prime factorization of this denominator. So let's find that. So this is just 5 times 3. So 3 and 5 prime numbers. So that's sufficient for us. What about 24? 24 is 2 times 2 times 2 times 3. So this is 24. So using only prime numbers, you can write 24 as 2 times 2 times 2 times 3. So this is 2 to the third power times 3, and this is just 5 times 3. So these are the prime factorization of the denominators. So now we need to compose the least common denominator. So let's do that now. We're going to compose the least common denominator. So what is the least common denominator? Usually we start with the first denominator. So we just write 5 times 3, and then you just check the second denominator and see what factors are not already in the least common denominator. You can see that 3 is already here, so you don't write 3, but 2 is not here, so you're going to write 2 to the third power. So again, you start with the first denominator. That's the way that you start composing your least common, and then you start adding the factors that are not already in the previous factors. Or if you have the factor already here, you just check the power. If the power is lower than the one that you have now, you just increase the power. So finally, you just complete this operation. So you're gonna have something like 5 times 3 times 8. So this is gonna be 120. So 120 is the least common denominator for these denominators. So now we're gonna finish our work by rewriting the fraction by using the least common denominator. So we're gonna have now that we have 1 over 15, and we're gonna multiply 1 over 15 by something, plus 7 over 24, and we're gonna multiply 7 over 24 by something. So you can see here that sometimes working with the final answer is not the best way to find these missing factors. It's better when you use the factor form of the least common denominator, because you can see here that 15 times something is going to be 120. 15 is already 5 times 3, so you know that the missing part of the least common denominator here is going to be 8. So you're going to multiply by 8 both the numerator and the denominator, because you have 5 times 3 is 15, so the missing part is just 8. On the other hand, when you have 24 here, you know that 24 is 3 times 8. So this is 24, so the missing part to get 120 is 5. So you write 5 here. So now you're going to be able to write this. 8 times 1 is going to be 8. 15 times 8, you know that is 120, because that's the least common denominator. Plus 7 times 5 is going to be 35, and again 24 times 5 should be 120. So now our problem has two fractions with the same denominator. So my common denominator is 120, which is the least common denominator, and I just need to write the sum of the numerators on the top, then proceed with this addition. You're going to find this to be 43 over 120, and that's it. So now you're going to work some exercises from the corresponding section. So this is going to be 1.2 exercise set on page, let me see what page. So this is on page 29. So there are a lot of exercises. You need to work as many as possible, but I'm going to suggest some of those. So let me write first the exercises. So we have 68 5 over 13 plus 2 over 13. Then 70 is just 5 over 16 plus 1 over 16. And then we have 76. This is just 17 over 5 minus 2 over 5. And then we're going to start with 78 1/3 plus 1/5. Then we have 80. 80 is 2 over 5 plus 2 over 15. Then we have 84 is 17 over 18 minus 4 over 9. Then we have 86, 3 over 2 minus 2 over 3. And finally, 88 is 7 over 30 minus 5 over 24. So I at least work on 88, 80, and 70. at least solve these 3 exercises, and you're going to include them in your final submission once you finish watching this lecture. So you're going to have just a small break to work on these exercises, and then we're going to resume this lecture. Now we're going to start section 1.3 on page 32, which is about the real number. So this section is just about some terminology that we need to learn to be able to understand future chapters. So this is about numbers. So the first thing that we need to know is the definition of the natural numbers. The natural numbers is just those numbers that we use to count. So anything that any result of counting is going to be a natural number. So you usually use this n, this calligraphic n, to indicate the set, because these are going to be sets of numbers, so collection of numbers. So, and we're going to use curly braces to indicate that we are dealing with a set. So for example, the set of natural numbers is written in this way. You use this n from calligraphy. You use your curly braces here to open and to close the set, and then you enumerate the elements of the set. So the first element is just 1, then the next element is 2, then 3, and so on up to infinity. So these numbers were used for the first time by human beings in ancient times to count things. So, and this is the first set that ever existed in math, so the set of natural numbers. So then one culture came up with another number that were missing in this original set when they were counting things. So the number that represents nothing. So the number that represents nothing is 0. So when you add 0 to this set, then you get a new set. That new set is the set of whole numbers. So in other words, the set of whole numbers is just the natural numbers and 0. So this is written just by adding or including the number 0 before 1. So then this is the set of whole numbers. We don't have a calligraphic letter to represent whole numbers. Then we have the set of integers. The set of integers is when we have the whole numbers and also the negative value for every natural number. So when you have this another set, which is going to be represented by this z, is going to be the set of numbers that go from negative infinity, so all the negative numbers up to -1. Then you have 0, and then you start with the positive natural numbers. So these are the natural numbers. These are just positive integers. Then you have from here to the left the negative integers, and finally 0. So negative integers, 0, and positive integers is what makes the set of integers represented by this letter z. So we're going to solve the first example. The first example from your book regarding numbers is going to be an example 1. And so example 1 is on page 33. And it's going to be just a kind of word problem. Where we're going to do some translation. So we're going to start doing some translation from English to algebra. So we need to write a negative integer that describes each of the following situations. So when you have something like a debt of $10, so how do you represent this in algebra? You're going to use a negative integer, so you're going to write -10. So negative, in this case, stands for the word debt. So when you owe money, you are in the negative side of the integers. Another translation that we need to understand is when we have, for example, the shore surrounding the Dead Sea. The Dead Sea is 1312 feet below sea level. Below sea level. So how do you write this in algebra? So the same way that depth was used to include the negative sign here, in this case the word below is going to be used to include the negative sign here. So negative 1312 feet is going to be the number. So okay, so now I'm going to talk a little bit about the graphical or visual representation of integers by using the number line. So this is going to be the number line that we're going to use to represent integers. So when you have integers, you are not using the entire number line, so you're using parts of the number line. What parts? Only dots. So we have a dot representing 0, we have another dot representing 1, then another dot representing 2, another for 3, and so on, and the same thing for negative numbers. So this, you have a dot or you have a point representing every integer. So when you use only these parts of the line, so you are not using anything between 2 points. So you are not using anything between 2 points. Those parts of the line at this point don't have or don't make any sense for us. Only these marks here are the ones that have meaning. So the meaning is that they are representing integers. So these marks, these points, so the points represent integers on the number line. And these points representing integers indicate the discrete nature. This is the discrete nature of integers. Discrete nature. So discrete means is this, you can enumerate, you can see, you can visualize, you can distinguish one number from the other very easily. So they are very, very far apart, one from each other. So they can be distinguishable. So you see where -1 is, you see where -2 is. So that's the purpose of this number line for integers. So we're going to solve example 2. So example 2 is on page 34. And the problem is that we're going to graph the following numbers on the number line. So we're going to graph -3, then we're going to graph 4, and then we're going to graph 0. So to do that, you just need the number line. The number line, you need to indicate just the locations of the integers, the discrete values that represent integers. So let's say that this is 0, 1, 2, 3, 4, 5, and so on. This goes to infinity, this goes to negative infinity. So you have -1, -2, -3, -4, and so on. So for the first one, A, -3, you just draw a point, a dot here. So that's for this problem. That's the graphical representation of -3. Then for 4, you're gonna draw another point here. So that's 4, and finally 0 is over here. So that's the solution for this problem. So now we're going to talk about a new set of numbers. So because you see, you can see here that there are missing parts of the number line that also represent numbers. But what kind of numbers? So these parts that are missing now from our discussion are not integers, are not whole numbers, are not natural numbers. So what kind of numbers can be used to represent a value that is between -2 and -3, or a value that is between 0 and 1, or maybe between 2 and 3. So what kind of numbers? So the answer is going to be now here. So we're going to talk about another set of numbers. So this is the set, and I'm going to copy directly from your book. This is the set of rational numbers, and this is described on page 34. So, and we can copy directly here from your book. It says that the set of rational numbers is the set of all numbers, is the set of all numbers that can be expressed in the form A over B, where A and B are integers, so that's important, and B is not equal to 0. So we write this in this way. B is different than 0. So, and this is something that we already know. The integer A, is called the numerator, and the integer B, is called the denominator. Okay, so that's the new set. That's the new set that we're going to use to represent values between integers, those missing parts of the number line. So, and we're going to use the letter Q to represent the set. So the set is going to be, again, just fractions A over B for any integer A and B, but be different than 0. So, for example, we can have, this is a set, let's write, this is a subset of Q, just as an example. You can write, for example, 3 over 4. So that's a rational number. You can have -1 over 2, another rational number. You can have 7 over A, or you can have 100 over 100,001, and so on. Any fraction that you can write is going to be a rational number, as long as the numerator is an integer, the denominator is another integer different than 0. So what about the integers? Are the integers part of the rational numbers? So this is a very important question. Are the integers part of the rational numbers? What do you think? So can you write 5 as a fraction? So can you write phi as a fraction. If you can write phi as a fraction, then phi is going to be a rational number, and the answer is yes. You can write any integer as a fraction when you write the integer in the numerator and you use 1 as the denominator. So yeah, the answer is yes. Any integer is also part of the rational number set. And we have numbers that you cannot write as a fraction. So that's another set. So that set is the set of irrational numbers. Irrational numbers. So those numbers that cannot be expressed, that cannot be expressed as fractions a over b, with a and b being integers and b different than 0. So what is that set? We're going to use a p to indicate that set, and that set has, for example, pi, some square roots, like square root of 2, square root of 5, many square roots, and many other numbers. E, for example. E, the base of the natural log system. So, the reason that this is another set is because there is no way for you to express pi as a fraction, and there is no way for you to express square root of 2 as a fraction, and many other roots, cube roots. So there are many other numbers that cannot be expressed as fraction. And the set that incorporates all those numbers, rational and irrational numbers, is going to be a very important set. That's the last set that we're going to study. There are more sets, but those are going to be covering more advanced mathematics courses. So, but we have the set of the real numbers. So the real numbers, so that set is just the set with this R is going to be the set that includes the rational numbers and also the irrational numbers. So that's the set of the real numbers. So, and you can represent now any number that is on the number line by using a real number, either by using rational numbers or by using irrational numbers. So now we can say that this is now the real number line. So this is the real number line. So now you have any number here. So the integers again are here. The integers are here, but now numbers in between can be represented by using fractions. So they're going to be rational numbers. So for example, you can have here, this number is going to be 1 over 3. Or maybe you can have here, this number is going to be, let's see, 5 over 2, and so on. You can have here, this is -1, -3. So you can have here -1/2. And also irrational numbers. So you can have somewhere over here, it's very hard to find the right location, but you have pi. Or you can have also another number, like for example, the square root of 2 is around here, the square root of 2. So be careful with radicals. Be careful with the square root of something, because if you have the square root of 9, this is just equivalent to 3. So be careful. So this is the square root of 9 is an integer. It's also a rational number, but it's not an irrational number. So this is not an irrational number because the square root of 9 is perfectly exact, is 9. So you have now to solve some problems for the assignment corresponding to this chapter. And if you have time, just check table 1.2 on page 37. So this is something that you need to do. I'm not going to talk about that now. So you just need to solve one problem from 1.3 exercise set, page 42. You're going to solve problem 34. So problem 34, let me show you problem 34. Is on page 42. Oh, okay. Before that, I'm going to show you the table because maybe some of you don't have your book yet. So you can check that table here. Let's see. Okay. Almost. Okay. This is table 1.2. It's just the sets that make up the real numbers. So natural numbers, some examples on the last column, whole numbers, integer, rational numbers, and irrational numbers. So this is just a summary of what we just mentioned during this lecture. So now in page 42, we have the exercise set, and you're gonna solve problem 34. So to solve problem 34, you need to read these directions. These directions are for these problems here. So if you have time, solve from 33 to 36. This is a good practice for you. If you don't have time, just solve problem 34. So what you're gonna do here is you're gonna list all numbers from the given set that are first natural numbers. So you look for the natural numbers here, then look for the whole numbers, then for the integers, then rational numbers, then irrational numbers, and finally real numbers. So solve problem 34. I'm going to write the set here. Is just -7, -0.6 with a bar here, then 0, then square root of 49, then square root of 50. So this is problem 34. So you're gonna find in the first path the natural numbers. So you're gonna see and say, oh, is 0 natural number? Is a negative number a natural number? No, these are not natural numbers. What about the square root of 49? The square root of 49 is 7. Is 7 a natural number? Oh, yes. Is the square root of 50 an integer? No. So the only natural number from this list is just 7. What about the next part? Whole numbers. Whole numbers are natural numbers, the positive ones, and 0. So we have 7 and also 0. So these two are whole numbers. Now, the next one is integers. So, and you're going to proceed in this way. So check the table, check the explanation. Again, you can rewatch the video as many times as you want. So I'm going to have you, so I'm going to give you a short time to finish this part, and we're going to start one more section to finish the lecture for today. Now we're going to start section 1.4. It's on page 44. It's about the basic rules of algebra. And the first thing that we're going to cover from this section is the vocabulary of algebraic expressions. So if you check the second part of this page, you're going to see here some terms that I highlighted, like, for example, terms, coefficient, constant term, factors of the term, like terms. So these are many words that we need to understand their meaning to be able to proceed with the next part of the course. This is important, so I'm going to write here for you. First, if you remember, an algebraic expression is something like this. There is no equal sign here, so this is not an equation. This is an algebraic expression because it's, in some sense, using letters to represent numbers, and it's using numbers, and it's using operators to indicate operation, like, for example, this plus sign indicates an addition, this minus sign indicates a subtraction, this little number 2 on top of this x indicates a power. So we're going to cover in some chapters later about exponentiation. So this is an algebraic expression, but the algebraic expression can be broken in pieces the same way that you can break a molecule in pieces. So you remember the atom is the basic unit of matter in chemistry, or the cell is the basic unit of an organism in biology. The same way in algebra, a term is going to be the basic unit of an algebraic expression. So how do you identify terms? Terms are usually separated by pluses or minuses. So here you have this plus, another plus here, and a minus here. So what is in between are the terms. So you're going to say that this is the first term, the first term. And the sign that precedes the term is the sign that corresponds to that term. So this minus goes with this, the plus goes with the expression that is on its right. So this is the second term, and finally this is the third term. So when your term doesn't contain variables, you can say that this is a constant term because there are no variables involved in this term. When you have variables like this, these are variable terms. Variable terms. So we have two variable terms. We have a constant term. So again, a term is the basic unit of an algebraic expression. So now let's inspect a term to learn more terminology. So I'm going to write now the first term here. So I have negative 3x squared. So this is a term. So what are the parts of this term? So this is a term. It's a variable term because it contains a variable here. So this is the variable. And also when you have an exponent, you also call this the base, and this is the exponent, and both the base and the exponent are a power. For example, this is a power of x. Now the number that is in front of the variable, you call this number the coefficient. This is the coefficient including the sign. So the coefficient is -3 in this case, and finally this is the sign of the coefficient, which is the sign of the term. So these are the pieces of a term. So, and also you have here -3 multiplying x squared. So these two are factors, the factors of the term, because they are multiplying to each other. So this is the first factor, this is the second factor. If you had something like 4xy, then you can say that 4 is a factor, x another factor, y is another factor. Another important thing to distinguish or to understand when we are dealing with algebraic expression is like terms. So what are like terms? Like terms are terms, so these are terms that contain the same variable, the same variables at the same power. So this is important. So to have like terms, the coefficient doesn't matter. So, and this is important because later we need to learn how to identify like terms, because you're gonna need to combine like terms to simplify algebraic expression. So we're gonna solve example number 1. Example number 1 is on page 45, and it says use the algebraic expression 4x plus 7 plus 5x to answer the following questions. So let's write the questions. The first one is, how many terms are there in the algebraic expression? So how many terms are there in this algebraic expression? So you need to check the pluses or minuses to identify the boundaries of the terms. So here, what is in between is just 7, then to the right we have 5x, so this is one term, another term, another term, so the answer is 3 terms. So the second question is, what is the coefficient of the first term? So what is the coefficient of the first term? So what is the coefficient of the first term? First, what is the first term? So we need to write the first term is 4x. So this is the variable, and this is the coefficient. So the coefficient is 4. The coefficient of the first term is 4. The next question, what is the constant term? What is the constant term here? You can see here, this is a variable term. This is another variable term, but this is a constant term because you don't have any variable involved. So 7 is the constant term. Finally, the last question is, what are the like terms in this algebraic expression? The like terms. So you have 4x plus 7 plus 5x. You can classify this. You can have 4x and 5x on the first column, 7 on the second column. So these are the like terms, okay? Because they have the same variable and the variable is also at the same power. What is the power of this x? The power is just 1. We don't write the 1 when you have these kind of variables. So these are the like terms. So the answer is 4x and 5x. So those are the like terms. Okay, so now we're going to talk about equivalent algebraic expressions using this the same example. So let me use this 4x plus 7 plus 5x. This is my algebraic expression. So we learned that 4x and 5x are like terms. So we can combine these two. So we have 4x plus 5x plus 7. So I'm writing these together because they are like terms, and I can combine them. So what is 4x and 5x? That is 9x plus 7. So now I have two algebraic expressions. So this is my first algebraic expression, and this is my second algebraic expression that resulted from combining like terms, and these two are equivalent algebraic expressions. Equivalent algebraic expression. So equivalent algebraic expression is described on page 45 if you want to read more about those. But the two algebraic expressions that have the same value for all replacements are called equivalent algebraic expression, is what your book says. So then we're going to learn about properties of real numbers and algebraic expressions. So I'm going to summarize these properties. I'm going to show these properties for you directly in the book. There is one that is very important and that we're going to need to learn very, very, very well. So properties of real numbers and algebraic expressions. Algebraic expressions. This is on page 46. So this part of the section is important. There are two properties that are the commutative properties. Commutative properties. So there are two. There are for addition and there are for multiplication. For addition and for multiplication. So we can understand this just by writing that a plus b is the same as b plus a. And also in the case of the multiplication, a times b is equal to b times a. So in other words, if you switch the order of the terms when you are adding terms, the algebraic expression is the same, it's equivalent. Or if you switch the factors in a term, the answer is the same, so that's equivalent. So that's one property. Then we have the associative properties. The associative properties, again, we have associative properties for addition and for multiplication, and this is just that you can combine in different ways, and at the end the answer is going to be the same. So when you have three terms, you can combine first the first two and then the last one, or you can combine first the last two and then the first one. The answer is going to be the same. The same thing with multiplication. You can multiply the first two factors and then the last one, or you can multiply the last two factors and then the first one. The answer is going to be the same. I'm not going to spend a lot of time in this because I want to focus in the most important property, the distributive property. The distributive property. So this is a very important property. So I'm going to write, in this case, everything that is expressed in your book. This is on page 49. So we're going to write here, let A, B, and C represent real numbers or algebraic expressions or algebraic expressions. If you have A multiplying B plus C, you're going to apply the distributive property of the multiplication over the addition. So we're going to write that the multiplication distributes over addition. And what is the meaning of that? Is that you can multiply this by this, so you're going to get AB, then you have the addition, and then you have the other product, A times C. So this is the distributive property. When you have an addition that is multiplied by a factor, then you can distribute that factor over the terms of that addition. So in other words, you're going to break the parentheses and you're going to match the factor to every single term inside of the parentheses. So A multiplies B and also multiplies C. So this is the most important property. If you understand this, that's half of the course, because the other half is going to be doing the opposite operation. When you have this expression and you are able to recover this expression, that's the other half of the course, and this is important. This is factoring. Factoring is when you go from right to left in the distributive property. So the opposite of the distributive property is factoring. So this is something that we're going to cover in one chapter. This is a very, very important operation in mathematics. It's a very important use of the distributive property. So let's work some examples using the distributive property, which is the most important part of this section. And then you're going to have problems to solve, and that is going to be the end of this lecture for today. So we're going to work two examples, and then I'm going to assign you your work. So let's do this. So we're going to work example 6. Page 49. So we're going to multiply 6 and x plus 4. So we're going to apply the distributive property. Apply the distributive property. We don't say of multiplication over addition because we imply that. We just say apply the distributive property. So this is a long name. So if you are very rigorous in your math vocabulary, you should say apply the distributive property of multiplication over addition. But in this case, you say apply the distributive property. So we're going to write this, and by applying the distributive property, we mean that we're going to multiply 6 and x and 6 and 4, and we're going to respect the sign here. So we're going to have 6 times x plus 6 times 4. So we are having this number repeated as many times as many terms are inside of the parentheses. So then we simplify. So 6 times x is just 6x, and 6 times 4 is going to be 24. So that's the first one. And then we have example 7 on the same page. Now we're going to multiply. We're going to multiply 5 and 3y plus 7. So again, we're going to apply the distributive property again. So we're going to have 5, 3y plus 7. We're going to multiply 5 and 3y and 5 and 7. So we're going to write 5 times 3 times y plus 5 times 7. So I'm writing 3y as in a factor form to simplify my results, because when I multiply, what I need to multiply is just the number. So 5 times 3 is 15. And then we have y plus 5 times 7 is going to be 35. So this is what we're going to cover for this lecture. So I'm going to give you an assignment. So this is from 1.4 exercise set. This is on page, let me see, on page 53. So I'm going to write the problems. There are 6 problems, and I want you to solve all the 6 problems. This is important. Remember, this property is very important. You're going to apply the distributive property in all these cases. So you have 4 times x plus 6. Then we have 9 times 2x plus 5. Then we have 1/4 that multiplies 12 plus 8r. Then we have 34, where 7 multiplies x plus y. Then we have 36, where 4 multiplies x minus 5. And finally, 46, where 4 multiplies 5x minus 3 plus 7y. So you're going to solve these problems. And once you have this problem solved, and the previous problems that I assigned before, especially the ones I marked with the star, in this case, all of them are marked. So meaning that you need to turn in all this work. So you're going to take screenshots, as I mentioned in the previous lecture, by using your phone, using an app that is known as CAM scanner or PDF scanner. The purpose is that you're going to get a PDF file. You can get just one or many, as long as you are able to submit them by clicking the submit button in the corresponding assignment, in this case, classwork 1B.